Yes, I'm Christina Karousatou. I'm from Wings, and I'm going to present the work that we've been doing with Konstantinos Lesis, my colleague who unfortunately could not be here today. The work that we've been doing within confidential 6G project, and the title that best suits, let's say, describes our work is the process of designing a fully homomorphic encryption scheme to encrypt the information exchanged in a federated learning model. So the agenda of the talk today is first to give you a description of the classification problem that we're looking at, then the classification techniques that we have seen without taking into consideration any security aspects, and then the results that we have within classical machine learning problem techniques, then adding federated learning to add security to our enhance the data privacy in our problem, and then is to see the results that we have in that, and then the fully homomorphic encryption scheme that we see into adapting, and then the conclusions on our work so far. So the classification problem that we look is is related to the use cases that we showed earlier today regarding confidential 6G project. The first one is regarding predictive maintenance for airline consortium using blockchain-based data sharing platform and federated AI ML orchestration, where here the general idea of the project is to build a platform to enable secure data sharing and between airline companies, aviation companies, manufacturers, regulation bodies, and other organizations. And the main goal that we look at is to enable predictive maintenance driven by AI and federated learning in order to preserve data privacy. And the other use case, the other problem that we look at is the one related to intelligent connected vehicles, mission-critical services, and over-the-air updates with FL and vehicle-to-infrastructure communication. Again, the bigger picture for this problem within the project is to provide mission-critical services within the context of secure vehicle-to-infrastructure communication, to provide over-the-air secure vehicle system updates with distributed learning. And what we do, our goal is to collect data from connected vehicles in order to develop federated learning models that will enhance road safety and driving experiences by supporting driving decision making. Okay, so these are the two problems that we look at. In this talk, we're going to discuss only about the connected vehicle, but the same work also goes for the airline with the engines of airplanes. No. Okay. Okay. Without taking, like I said previously, without taking into consideration any data privacy, the way to go for that is we chose to use random forest classifier to solve this problem, which is an ensemble learning technique, and it combines multiple decision trees, and this allows us to have higher accuracy and to reduce overfitting, and it's widely used for classification tasks. The benefits, how it works, just a brief reminder of how random forest classifiers work. Of course, they have two phases, the training phase and the prediction phase. In the training phase, we use random subsets of features, they are created and data points, and individual decision trees are built using these subsets. And then in the prediction phase, a new data point is passed through each tree in the forest, and then each tree makes a prediction, and then we take the majority vote to determine the final class label. Why we chose random forest classifiers? It's because they provide high accuracy. Since we have multiple trees, yes, in comparison to single models, it gives have more accurate predictions. This also provides reduced overfitting. Random selection of features and data points during training helps to prevent the model from memorizing the training data, and it generalizes well to unseen data. And also it handles well missing data, and also it's robust to outliers. So the presence of outliers in the data has less impact on random forests due to the averaging across multiple trees, again, as opposed to a single model. The data set now that we've used on traffic, driving style, and road surface conditions, it contains parameters acquired by cars via OBD2 scanners. The dataset were collected by 2 cars. And so we have two types of problems. The first one is regarding the traffic congestion conditions, and the other one is regarding the driving style of the driver. So we have, for the traffic congestion, we have 3 classes that a data instance we want to classify it. It's the low congestion condition, the normal congestion condition, and the high congestion condition. And regarding the driving style, we have an even pace style and an aggressive style for the driver. The features that are included in this data set are this list. It includes altitude change, current speed value, the speed variance, the speed variation, longitudinal acceleration, the engine load, engine coolant temperatures, the manifold air pressure, the revolutions per minute, the mass airflow rate, the intake air temperature, the vertical acceleration, and the average fuel consumption. So all these are the features that are included. So for the classical machine learning algorithm, using a random forest classifier, for the problem of predicting the traffic congestion, the accuracy of our model was 0.9. And for the driving style prediction, the accuracy was 0.83. Now, so this is the simple, the classical machine learning model. Now, moving on to federated learning, so that we enhance the data privacy. Luis previously explained very well what is federated learning. Just a small reminder, it's a decentralized machine learning technique. It trains models on the data that are stored on individual devices. There is no need to upload the raw data to a central server, and this way we have data privacy. So the data are not transmitted back and forth between the parties and a central server. So the benefits of federated learning is that we have enhanced data privacy, like I mentioned. It enables training on sensitive data, so parties do not expose, if they have sensitive data, they do not expose them. It has an improved model generalizability, and because of this, avoiding this back and forth of transmitting data, we have reduced data transfer costs. Now, the framework that we've used for federated learning is Flower. The reason that we chose that framework is because it's flexible and customizable. It supports a wide range of machine learning frameworks, like PyTorch, TensorFlow, etc. It is easy to use. It has a user-friendly API that simplifies the process of building and deploying the federated learning systems. It is scalable, which is we have to take into consideration if we want to deploy many vehicles in our solution. And then it also has rich experimentation features. Now, so the results that we got for using federated learning, again, by deploying a random forest classifier, for the traffic congestion problem. The accuracy that we got is 0.87 as opposed to the classical ML model's accuracy that we got that was 0.9. And then for the problem of predicting the driving style, the accuracy that we got is 0.81 as opposed to 0.83. So we see by adding federated learning, we don't have a big toll on the accuracy. So it is a very small price to pay, let's say, for adding data privacy to our solution. So now the next step on top of that is that what we look for is to add on top of that fully homomorphic encryption. And by fully homomorphic encryption, what is fully homomorphic encryption is a technique that enables computations on encrypted data. It supports addition and multiplication operations on ciphertexts, and the encrypted results can be decrypted to reveal the original outcome. And what we mean by that is that if we have two integers, x and y, and if x plus y equals z, then encrypted x plus encrypted y, it will equal to w, let's say. And if we decrypt w, then it will be equal to z. So, yes. So if we apply fully homomorphic encryption in federated learning, it will encrypt model updates on the individual devices, and then the model updates that will be performed in the aggregator, it will be on encrypted data. The data will never be revealed, even for the model parameters. And so yes, aggregates encrypted updates to create an improved encrypted model, and then it preserves data privacy even on the devices and during communication. Alas, I mean, it's a very nice and powerful tool, fully homomorphic encryption, but it has a cost. It requires high computational overhead. It has increased communication costs and potential accuracy limitations. So this is what we want to see, because there is a trade-off between the extra data privacy that we have in our solution, but we need to see what is the toll that we have to pay if we add this. So to conclude our findings so far and our next steps, we see that the federated learning model has slightly lower accuracy compared to classical machine learning model. But like I said, like we saw, the difference is insignificant. So federated learning should be preferred when data cannot be shared due to privacy reasons. It can be federated learning. It can be combined with fully homomorphic encryption in order to ensure secure communication between server and client. But it's this is our next step. Like I said, is to see this trade-off, to calculate the computational cost that FHE adds to the model, and also the accuracy, if it has a cost also in accuracy. So I think I was talking fast, and I finished earlier. Thank you.